Hello to you all and welcome to this topic webinar. Thank you for joining us today. Apologies for the slight delay in getting started. So I'd just like to draw your attention to the fact that we'll be recording this webinar and a copy of the webinar recording and a data set will be made available, which will be on our forum. You can send us questions during the presentation. Please use the Q&A function to do this. We won't be so closely monitoring the chat, so if you ask questions in chat, we may miss it. So just remind you to please use the Q&A function for questions you'd like to direct to the presenter. And please do join our X-ray forum. As I said, we host the recording and the data set there. The other topic webinars we've done in schools and workshops are all available via the forum as well, so it's a very useful resource. Okay, so with that, I will introduce our speaker for today. So today's speaker is Dr. Jakub Wojciechowski, and he's an application scientist in our lab in Frankfurt in Germany. So today he's going to talk to us about diffraction methods for MOF investigations, and I'll pass over to you, Jakub, so please take it away.
Thank you, Fraser. So, yeah, I'm today's speaker, but lots of this work was done by Dr. Hypix-HE, which is also a colleague here in the office. He's specialized in powder diffraction, so it will be kind of a big application talk, but I want to include him also on his first slides, as you will see that he contribute a lot to this talk. So just to briefly give you outline what instruments and what methods we will eventually show, RIGAKU has a full line from benchtop single crystal instrument to Synergy that allows users to do single crystal measurements from 300 microns and bigger to sub-micron crystals. And of course, RIGAKU also has a branch of XRD instruments, and here I'm showing the free one that will somehow show in this talk, the benchtop MiniFlex, SmartLab SE, and SmartLab XE. And the most of the talk today will focus around those triazole MOFs that, as you can see from the citations, are part of Dr. Hypix-HE research, that he brought them to our lab from his university, and we have them available and we're using them for trainings, instrument preparation, application tests, and presentations. So basically, we try to develop new methods, teach ourselves so we can pass this to our users. And this is kind of a story of this kind of challenges or that Maciej tried to set up for Synergy and how it was actually solved from me and solved. So if we think about application diffraction methods for MOF materials, the primary one is a crystal structure solution. That's obvious. And for a very long time, we all know that synthesis and crystallization will decide what you can do. If you are patient and you know how to do it, you can run the crystallization, co-crystallize it, you get beautiful crystals, and you can use a single crystal instrument to solve the structure. If you need to do it in bulk or very quickly, for whatever reasons, because you want to run lots of different kind of synthesis, you end up with the powder system. And then very often a skilled crystallographer will go for crystal solution from the powder data, which is not so intuitive, easy, and not so much well accepted by community like single crystal data, but still very valid information. And with the SmartLab Studio, you have access to direct methods, charge flipping, and it will provide the same structure model as a single crystal instruments. And this is an example of one of those MOF, the the copper one that was sold from powder data in the SmartLab Studio, a little bit close up. Picture too small, and that basically can be done even on a benchtop instrument. So I could not really believe it. Then Maciej just showed me now, 20 minutes of powder data collection. It's a cool small device, a small circle giving very short beam path, giving advantages of high intensity, short measurements, and with proper setup of all the solar slits and some filters from nickel, you could get enough quality of data to actually solve a MOF structure if the sample is good diffracted. So I thought, why? So if MiniFlex can do it, then probably I can do it also on Synergy. So of course, those are single crystal instruments focused mostly on flux and point focus operations. So we have a Montal optics, very high flux, but we have what we will point out, talk later, divergence slits or divergence control slits. And we have also Hypix 6000. So Maciej gave me a challenge that it should take less than an hour because he thinks that this is what he usually measure. But of course, the beauty of this method is that I don't need a huge size of the sample, but a really tiny amount. And how the data look? So the blue one is from MiniFlex, and the red one is from Synergy. So this is kind of close up to show you the results. And this is the frame from that measurements. I used what we call Gandolfi scans, so to smooth out even more the powder. So it is the same technique that moves phi and omega block at the same time to randomize the sample rotation. A little bit took me less than an hour. As I mentioned, beam slit setting was set up to 2% of intensity of the beam, still giving very nice diffraction, nicely adapted port. And on top of this table, you have a peak statistics for Synergy on the bottom on the MiniFlex. And as you can imagine, there was no problem of solving this structure from that Synergy data. But probably I should be ashamed that I still didn't learn it because I had I will show you later how I actually did it, because I didn't solve it myself. But as I promised, I want to just point out the importance of the divergence control on PhotonJet sources. So be able to decrease peak overlap or control mosaicity of your spots in the MOF research, either is powder or single crystal, is quite important. The MOF very often will have a large unit cell with significant volume, which can cause overlap, especially if you ever measure single crystal MOFs. You know that the quality of this crystal is not always perfect. And very often the spots are overlapping. And because they are very often also very weakly diffracting, you are not very willing to move the detector a little bit back. So you would like to keep the detector close as possible. Then the ability to tune in your source and stop the spots overlap or make the spots looking better, it's a crucial thing, and it's a very cool RIGAKU solution that is available for XtaLAB Synergy platform. So I mentioned that I kind of cheated, and this is how I cheated. So when I was mounting this powder, as you can see on the loop, I noticed that there are some parts that are not really yet powder. So I can mount such a batches of 20 microns of powder and screen them, and some of them will show a pattern. This is a warp image from about 3D that clearly shows very poor quality, but still the discrete diffraction pattern. And that was enough to run what we have in our software, XtaLAB Pro, what it is experiment measurements. It also took me 1 hour, so similar to that powder measurements in 100K, and it solved without needed to learn how to solve the structure for powder. So Maciej was kind of disappointed in me that I kind of cheated, because he really was hoping that I finally learn how to measure the structure from powder. So back to the topic, another very important technique or combination of technique is variable temperature studies. And this is connected to testing MOF stability in a wide range of temperature. For industrial application of MOF or as a functional material or catalyst, you need to prove that the framework will remain properties. Or if you're dealing with porous materials like breathing MOFs, or you activate the MOF and you want to be sure that it's empty, you really have to nicely describe that also. So the same MOF that we still have in lab place have quite nice temperature change. It high temperature. It goes to cubic version without changing significant structure. The coordination spheres are just more symmetric, and it is noticeable in powder diffraction, and those are solutions from powder diffraction done by Maciej. And what Maciej like to use for such a research are REACTOR-X, which is infrared heated reactor, which heat up very quickly. You can heat up 300 Celsius per minute. You can go from room temperature to 1000 Celsius. And what is important that you can introduce corrosive gases. So if you're doing something with your MOF and you need a hydrogen there or some other oxides, you can still introduce this to this chamber and run the variable temperature studies with your MOF sample. So this is an example of how the analysis would look on this SmartLab seal tube system with DTEX detector. Maciej perform and show that the change is actually reversible and characterize exactly the range when you can expect this change. And I was looking on the spot and realized, okay, but you're missing a bottom part, yes? You don't have a low temperature. And he said, yes, but because low temperature devices are not very popular on XRD devices, but they are kind of standard devices on all single crystal instruments. And there is really no problem of running either powder or single crystal variable temperature studies with Synergy system. We can mount both an helix and cryostream, also hot blower, giving us the full range from 20 to 1000 kelvins. And as I mentioned, the plus version of cryostream can cool and heat. So you have a decent range of 80 to 50 kelvins with the cryostream 800. And also I just want to mention that if you really want to do even push a little more, you can equip our system with a sample holder called TOPIQ, which fit under the cryo, and you can do even high pressure with variable temperature on your MOFs. So some unique feature for single crystal instrument. So I took this powder MOF and I ran it, as you can see, even today quickly, and as you can see extremely quickly, because each scan was only 23 seconds per scan, because I used the Synergy DW copper. So this is version of Synergy R, our rotating anode system with dual wavelengths anode, and I also use a slit control to lower divergence to get the slits. And of course, as Maciej informed me that there was no change, no chance that there was any phase transition, although that we noticed some intensity distribution changes, which was expected with cooling down the sample. I record you a movie on different powder done for you to show you how that looks. So this is like the proper measurement done with the Kapton tube enclosing the sample of powder. As you can see that the instrument is just starting collecting data. There's Hypix-6000 mounted, which just collects data. So you can see that there are lots of spots. So inside this powder, you still have microcrystallites. So probably for good data, you should use like a Dolphy scan, and it will just finish. Let me just skip to it further. Go to the parting position, and then advance one temperature point, which I asked him to do, and then he will go back after reaching the temperature and repeat the scan itself. I use the IGH, which in case that if the cooling was out of the state, should keep the sample center, although with this such a big capillary, there was no reason to do that. But you can do that on a small molecule, on this single crystal instrument also the same, and actually observe the change of the if existing phase live on single crystal instrument very reliable. And this is our SilTube system, S system. So the exposure times are still very data collections are quite still usable and reliable. So each scan was only a minute and a half to reach 60 degree from 5. You can see a small Kapton bump on the Mini, so you can see how the detector is sensitive. You can even spot the Kapton bump, and you can see that the pattern remains stable for the whole range of minus 170 degree Celsius to 60. Of course, the nitrogen was used as an atmosphere for this experiment. So the unique thing that I think that single crystal instrument always is winning is possibility to solve a small crystal or activated MOF. Very often, when very nice crystals, if they have a solvent inside, and you go through the process of activation, they just will crumble and fall apart. And in the end, you end up with very small objects. And very often, people just go to powders straight away. But with the powder structure solution, you don't really have a chance to make sure that it is activated, the MOF is activated, or calculate, see if it's actually fully clean, because the structure solutions are not so much reliable for such a precision of questions. So you can see this is one of the MOFs that we have also in lab. It's a slightly different ligand, or basically different ligand, not slightly different ligand, but similar, coming from the same research group that Maciej belonged. And I used Synergy S. It took me a day to measure, full day, 27 hours to collect 100K. But yeah, it solves, and I could easily show by using a squeeze mask or bypass in OLEX to actually check if the DMF is still there in that crystal structure or not, because I've seen some very low level residual density in the Fourier map, but just to be sure, I can easily say that it was activated, because it basically the amount of the electrons is not significant enough to call it a different molecule. And we go to what I think is the biggest curse of MOF research, that some MOFs just diffract, or not diffract at all. And this was something that Maciej was hoping that will force me to go back to powders. Again, this is this thiazole MOFs, but with iron, and he worked on this because it's quite interesting material. It has high temperature change that change unit cell, but not the space group. And it is interesting because it's a spin crossover transition, changing the material actually properties. So it is quite well known and studied material, but for good reasons, there are not available single crystal solution for those crystals, because they are extremely small, quite weak diffracting. Of course, Maciej solved them with the powder. Here are the distances of the coordination bonds, showing that match the proposed speed crossover transition, and they are both cubic, and I just changing the dimension of the cell. So he very often say that the best instrument to do with powders for weak MOFs is our SmartLab XE with rotating anode, also 9 kilowatts power. You can use a very small amounts of samples. You can use our RIGAKU made XRD DSC attachment with radiation that you choose, and the goniometer that you can see on this picture also have the possibility to mount the Hansen attachment monochromator. So it's a user mounted option that if you run a problem with indexing for solving, because you have to index pattern before you even start solve, you can just monochromize the beam and get extremely good pattern quality to deal with challenging samples from powder solutions. So the attachment for scalar calorimetry works with small amount. We can use heated gas also, or static air in a gas with this attachment. So it's quite nice attachment, allows you to do lots of experiment, and we can go from minus 40 to 350 degrees of heating and cooling. And this is the example from this iron small MOF, and you can see that the change is fully reversible and really nicely visible. That it was 2.5 minutes per scan, 5 minutes of holding time, nitrogen as a atmosphere. So Maciej gave me this powder and said, try to solve this one. So obviously I asked him if he has nice picture of the crystals, and he has, and I saw that there are some larger crystals there in that powder, but none of them really diffracted or show any signal on Synergy S. So I thought, okay, I will use Synergy R, or in case Synergy W. We currently have a version with the robotic sample changer. I will just mount hundreds of those batches of the powders, and I will find some single crystal out of it. And I start doing that, so you can see that this is a picture from microscope. It's literally very, very fine powder. I was mounting those batches of the crystals, and with our Synergy DW, I start seeing some spots, and even more, and resolution was not bad. But I ran the problem that I could not index the pattern at the initial. So, and even with the robotic sample changer, it just was taking too much time to mount all those things together. So the project went on a back burner and say, okay, maybe later I will really sit down, mount hundreds of loops, and I will find that lucky one crystal that would give me enough good diffraction to solve it. And then we got a new toy in access in our lab, Synergy D. It's our brand new system, diffractometer based on electrons, built on CHALL 200 kV electron source. We have our own version of Hypix detector built for this, and of course it's controlled by XtaLAB Pro and supported by the RIGAKU single crystal instrument. And so I just packed the powder, send it to Japan, which is actually our the unit where our demo unit is now sitting, and asked Ito-san, thank you again, Ito-san, for some remote access. He loaded the sample for me, and I recorded myself for Batie showing that how I cheat again and not learning how to solve the structure for powder. So I found a small grain, quickly center it, so let me pause it, so you can see I tilting the stage to see how much offset in the Z direction MES, and then I just clicking on the image to adjust the Z stage, so the software center it is kind of semi-automatically. Then I'm just confirming that the grain is staying in the center, so it's center. I'm switching from visual mode to diffraction mode. I see nice looking spots, and from this point I have to just go through the standard Chrysalis Pro windows. I have to just put some information about the sample. I know basically what is the symmetry of the structure, so I choose a scan range 40 by 40, and I just go play. And this was cost 4 times the speed of the real measurements, but you can see that it will be just a minute when the system collects enough data to run the AutoChem on it, and with the kinematic approximation, I got the solution from the powder in rather of minutes and not hours, which was required even on rotating anode system. So here's the pattern that I observed, checking if the grain is clean and there's no other strange effects. And yeah, and there is a solution already ready for me in the window. So let's move a bit further. So you see the pattern, and he will be done in minutes. Yep. Solving again in the proper space group, which of course Batie already found earlier. And then those are results. This is of course a kinematic approximation using OLEX and Chrysalis Pro 2, but it was not bad. And we're still discussing the distance of coordination because the both distance are slightly different. We still have to check that. But I also found something interesting. I scanned, of course, more than one grain, and one of the grain show a very nice superlattice peaks. So I collected a longer data set on this grain, and I was able to find a possible superstructure, or just maybe the crystal or material start decompose with electrons. Because when we look on the coordination space, so in the structure predicted for powder, this is the same crystal structure but just different space, of course, larger unit cell. So the coordination falls around the now 6 iron atoms, not 2, are not much difference. So we're still wondering if it's actually a proper solution or just element of sample decomposing in the beam. And we discussed what to do with it. And we figure out that we can run third distribution function of this material. And I'm running out of time, so I cannot show you that we're still collecting data, but just to inform you that yes, on both systems you can collect with the silver radiation and Hypix-HE technology quite nice third distribution functions. And with this technique, maybe we will solve the mystery if in this MOF iron MOF there is more different coordination irons center, or only 2 as predicted for powder data. And it's first solution from Synergy ED macro ED experiments. So at the end, I just want to thank you to another great RIGAKU solution. So as you can see, there are different instruments, different sources, SealQ, but they all have a common denominator. It's Hypix technology, hybrid counting detectors that RIGAKU makes. And with that, I want to finish, and please contact us if you have any questions, and I can take a few questions now.
Thank you very much, Jakob. So we don't have any questions at this current time, but while we're waiting to see if anyone does want to ask one, just remind you, if you do, please use the Q&A function. So Yeah, I mean, Jakob, you have quite a lot of experience of doing these types of more challenging experiments. How do you, when you're using the Synergy, how do you feel about the difference between this and X-ray in terms of tackling these problems?
Means Synergy and SmartLab, or Synergy and Synergy D?
Synergy and SmartLab.
So for sure, this SmartLab is more like a robust system that allows you to process with more automation. We have a robot changer that will allow us to change more samples, but of course, if you have an industrial application, the SmartLab seems to be extremely good. But for research powder measurements, single crystal instrument nowadays, thanks for using the same kind of detector, having slit control, the divergence control on the copper source, are really catching up to benchtop instruments. And I was surprised how good and how much you can do from powder data from single crystal instrument. And I think also I surprised Maciej, showing him that that I can catch up sometimes even with the SmartLab with powder data from Synergy instrument. And basically, this is not the Synergy always wins when we're talking about a very small amount of material when you're talking about micro powder diffraction. So if you really fail to crystallize your MOF or your material, and you have some just leftover powder at somewhere at the edge of your glassware, you can still try to get some information out of this and just collect data, powder data on your Synergy system. And definitely the SmartLabs are the system that are so easily changed and have so much pull attachment that I really happy that they can just switch on, put slit calibration slits, and I think the biggest advantages of SmartLabs are this auto-align thing, that every time they change anything, they just hit the button in the software and both source, sample, and everything will align itself for perfect optimal instrument measurements.
So you may see a question just popped up in the Q&A. So the question is, what size of crystal from the powder are you able to get single crystal data on the Synergy? So I guess the question is really what the smallest crystal you can get single crystal data from is.
From copper seal tube system, around, I would say, 10 microns, sub 10 microns on rotating anode. If I can mount 3 or 4 micron crystals, it is really easable. The more challenging is now mounting those crystals. We get an update on the microscope, but isolating them and mounting is a problem. So sometimes, as you show me, I just measure a cluster of microcrystals and just index one of the microcrystal then and do just crystal structure solution, and then I can measure on SmartLab powder and refine the solution of powder just to check if I have the same structure for bulk powder, and then I didn't pick up by accident one of the polymorphs or strength variation of your MOFs crystallites. But when you get into those few microns, the work is getting challenging, because even with the best microscope, mounting is the most consuming time and selecting the sample. And the biggest fun for me working with Synergy D is that on the grid and basically use a software, point and click, and I can check at the same hour and multiple grains as I show you. And most of the grains show one structure, and I found one lucky one that start acting slightly different. And now we have another challenge to try to figure out if it's just experimental mistake or there is actually some truth that this MOF can have slightly different phase also included inside mixed-in, or just change under conditions of vacuum or electrons. So that's the, I think, answer.
Thank you, Jakub. Maybe just before we finish up, you could say something briefly about the mounting of the powders on the Synergy. So you had, I saw in some of the pictures, the Kapton tubing as well as the loops, I think.
Yeah. So if I know that I'm measuring with low temperature, I will very often just use a loops, dial loops or Kapton loops that sometimes have more contact surface. Because if I can freeze the sample, then it will hold. If I will use room temperature or high temperatures, I will use a Kapton tubing because of a high chance that the sample will be just blown away from your holder. And then if you're doing just quick measurements, that can be enough. But if you want to do the proper analysis, looking for changes, you can then wondering if the shift of peaks is done by sample moving or the loss of intensity. Or so if you really want to do the variable temperature studies in non-freezing conditions, I would say the Kapton tubing is very nice solution. Glass capillaries also works. We know that they are just more fragile and you have to be more careful with. But we do support glass capillaries, and for example, per distribution functions measurements we do quite standard also with the glass capillaries. That just requires us to measure empty capillary again and subtract it from the sample. But the quickest way I do is always just use cryo and mount with the standard loop. So I don't spend much time with packing capillaries or even those Kapton microtubing when I have a powder challenge for Synergy.
Okay, thank you, Jakub. So I think we'll finish it up there. So thank you everyone for attending. As we said at the beginning, the recordings will be available after the event. So if you missed any part of this presentation or you want to share it to colleagues, then it will be on the forum later on. So thank you, Jakub, and goodbye, everyone.
Thank you. Bye.